In the last class, we have introduced the basic biochemical processes in anaerobic digestion, and the microbial communities perform these processes. Now we move forward to the design and operational considerations for anaerobic processes. Anaerobic systems do not require oxygen input. Therefore, biological oxygen demand is not applicable. Instead, biomethane potential is used to quantify biodegradable organics in anaerobic processes. Similar to BOD measurements, BMP experiments also mixes the substrate with the inoculum, and the cumulative methane production is measured over time. Warm water bath is typically used to speed up the reaction. In this figure, gas volume is measured by water displacement in a graduated cylinder. Because CO2 is produced along with methane, sodium hydroxide is used to absorb CO2, so the volume you read is just methane. We can also use gas chromatography to measure gas composition in the lab. In the biogas produced during anaerobic digestion, roughly 65 to 70% is methane, and the rest 30 to 35% is CO2 plus trace amount of hydrogen gas, nitrogen gas, hydrogen sulfide, and water vapor. From stoichiometric calculations, 1 kilogram of COD reduced can produce 0.35 cubic meter of methane at standard temperature and pressure. Can you pause and try to make this calculation yourselves? For 1 cubic meter of methane, its heating value is around 36,000 kilojoule. The biogas can be used to generate electricity and heat with combined heat and power systems. With the heating value of methane, we can roughly calculate how much electricity or heat can be produced from given waste stream using anaerobic treatment. For small-scale applications that cannot afford CHP systems, because methane is a much more potent greenhouse gas than CO2, the biogas is often flared to convert to CO2 to reduce the greenhouse gas emission. The biogas collection system can either be a flow cover or fixed headspace. The latter requires a gas storage chamber in case the liquid level in the reactor goes down and the gas needs to be sucked back into the reactor. In addition to the gaseous biogas that can easily be collected, there's also a substantial amount of dissolved methane in the aqueous phase. The liquid effluent from the digester is saturated, if not supersaturated, with methane gas. It usually is not practical to remove and recover that, so they are often lost to the atmosphere. To maintain a stable operation of anaerobic processes, pH is an important parameter to be controlled because different microbial communities in this multi-step process have different sensitivity to pH change. If the system pH falls outside of the optimum range, usually to the lower side, due to accumulation of VFA, the VFA consumption rate by methanogens can decrease, leading to further accumulation of VFA. This can snowball into system failure if it's not handled properly in time. One solution is to add alkaline such as sodium hydroxide, potassium hydroxide, sodium bicarbonate, and ammonium hydroxide. This can be one major cost of operation. You can also reduce the loading rate so that the accumulated intermediates can be degraded. This, of course, can disrupt normal operation. Bicarbonate in a reactor along with ammonia can provide buffer capacity that keeps the pH relatively stable, allowing the reactor to handle moderate pH accumulation resulted from loading rate variation. We can determine the alkalinity in the reactor by titration. A strong acid is added to a certain amount of sample until the pH reaches 4. This measures total alkalinity that includes bicarbonate alkalinity as well as VFA, which are weak acids with pKa higher than 4 and can provide buffer capacity at low pH. So, we can calculate the bicarbonate alkalinity by subtracting VFA from total alkalinity. The 0.85 and 0.833 are conversion factors from the VFA composition and the VFA to alkalinity conversion. An alternative method is to titrate the samples to pH 5.8. This accounts for about 80% of bicarbonate alkalinity and almost no VFA. If a facility can regularly measure VFA concentration, typically through gas chromatography or liquid chromatography, VFA to alkalinity ratio can be a good indicator to digestion stability. You generally want to keep that below 0.3. Temperature is another important parameter that can affect the reaction rate, particularly for anaerobic processes performed by slow-growing microorganisms. Typically, the reactors are heated to either mesophilic condition or thermophilic condition to achieve the 15-day SRT. If the reactor is not heated, a long SRT of 40+ days is needed to avoid biomass washout. A long SRT means a large volume for digesters with no SRT-HRT separation capability, hence high capital cost. Heat exchanger can be used to heat digesters, but a layer of sludge cake can form around the heat exchanger, reducing its efficiency. While it's difficult to service an internal heat exchanger in a digester, external heat exchanger can be serviced to mitigate the caking issue. Steam injection is gaining popularity as it has no caking issue. Designers and operators need to be aware that due to condensation, steam injection adds water to the digester that dilutes its content. Mixing is important because it ensures that the SRT, temperature, substrate, and inhibitors are evenly distributed in the reactor. A dead zone can reduce local reaction rate due to low temperature, inhibitor accumulation, and substrate deficiency, hence reduce the overall digester efficiency. Because of the high solid content, it can be challenging to achieve effective mixing in anaerobic digesters. We can recirculate the biogas to the bottom of the reactor using gas compressors and release the biogas using diffusers. As the biogas floats upward, it creates turbulence that mixes the liquid content. This is the most popular method for mixing. Some digesters use mechanical mixing such as propellers, while liquid recirculation is also often used, sometimes as a supplement to other mixing strategies. The shape of a reactor is very important for effective mixing. Traditional cylindrical or even square reactors are easy to construct, but can be difficult to achieve uniform mixing because of dead zones. Grease, sand, and grits may also accumulate as a result. Egg-shaped reactor can achieve effective mixing with relatively low energy input due to a superior hydraulic condition. Sand and grit won't accumulate because of its deep cone bottom. Its narrow neck can also reduce grease buildup at the liquid surface. And this shape requires less land area, but it is also costly and difficult to construct. Only a few companies can construct large-sized egg-shaped anaerobic digesters. Trace metals are required for anaerobic biochemical reactions as they are enzyme building blocks. Because the required concentration is so low, waste streams usually already contain enough of these trace metals. Trace metal deficiency is not a common issue. For some industrial wastewater, however, like brewery wastewater, trace metal may need to be supplemented if they are treated anaerobically. On the other hand, high levels of these trace metal can be toxic. The table shows the IC50, or the inhibitor concentration that reduces the reaction rate by 50% of various heavy metals. In addition to heavy metal, there are a few other compounds that can be inhibitory to anaerobic processes at high concentration. Cations like sodium, potassium, calcium, and magnesium are usually not an issue until their concentration are in the thousands of milligrams per liter. Once the biomass is acclimated to the high cation concentration, over 10,000 milligrams per liter of cations are needed to inhibit the anaerobic reactions. Moreover, different cation toxicities are antagonistic, meaning that the presence of different cations cancels out each other's toxicity. As we have covered before, fermentation products like free ammonia and free VFA are also inhibitory to several anaerobic bioreactions. Note that the free ammonia and free VFA concentrations are determined by both total ammonia and total VFA concentration, as well as the pH. We can use anaerobic toxicity assay to determine the toxicity of target compounds. We can perform the assay by dosing different amounts of those compounds of interest into a substrate inoculum mixture and monitor the methane production rate. We can plot out the results, and the slope indicates how toxic it is. This figure is an example dose response curve of copper. The most commonly seen conventional anaerobic digestion is a single CSTR with no SRT-HRT separation. Therefore, to achieve long enough SRT to avoid washout, a large reactor is needed to maintain a high HRT. The standard rate systems typically used by small plants are unmixed, can either be heated or unheated for low-cost operations, and their SRT can range from 30 to 60 days to achieve sufficient reaction. That single tank digests, settles, and thickens the biosolids. In a high-rate system, typically used by medium to large plants, the SRT is maintained at 10 to 20 days as the digesters are well mixed and are heated either at mesophilic or thermophilic conditions. After digestion, the biosolids are thickened in a separate process. Novel anaerobic digesters have been developed to increase the efficiency of digestion. Two-phase anaerobic digesters are one example that provide different growth environment for acetogenic bacteria and acetogens and methanogens. The first acid phase reactor has SRT of 1 to 2 days and a pH of 5 to 6, and can be thermophilic and mesophilic. This is beneficial for hydrolysis and acetogenesis. Then the second gas phase reactor is much larger and has SRT of 10 days and a pH of 7 to 8 to promote the growth of methanogens and the centrophic acetogens. Although a two-phase reactor is more complex to manage than a single CSTR, it has overall smaller footprint and higher flexibility in operation. Another example of a high-efficiency suspended growth anaerobic digester is anaerobic membrane bioreactor. Like the ideal biomass separator configuration that we study for aerobics treatment, it utilizes ultrafiltration membranes to retain biomass and particulate compounds through size exclusion and achieve high-quality effluent. This effective separation of SRT from HRT makes it possible to operate at a low HRT while maintaining a high SRT for thorough breakdown of particulates. Because of the long SRT, the reactor can be unheated to save energy. On the other hand, the membrane requires high transmembrane pressure to maintain its filtration flux, which can be energy intensive to maintain. Moreover, membrane fouling control strategy like scouring, backwashing, and even chemical treatment is needed to mitigate the membrane performance deterioration due to membrane fouling. Because some fouling is irreversible, the membrane needs to be replaced every 5 to 10 years. All of this add up to the maintenance cost. Also note that the methane solubility increases as temperature decreases, so a lower proportion of methane is collected in the gas phase as more methane is wasted in effluent liquid when the digester is operating at a lower temperature. There are a variety of anaerobic membrane bioreactors. For configuration, there are submerged and external membrane reactors. And for membrane type, there are flat sheet and hollow fiber membranes. In addition to the high efficiency suspended growth anaerobic digesters, attached growth digesters also have separated SRT and HRT and can be used for high rate operation. Anaerobic filter uses filter media to support the growth of biofilm. Although biomass can be retained to achieve high quality effluent, there are a lot of issues with its operation and performance. A long startup time is often needed for biofilm development, although it can be shortened if the right inoculum is used. Also, there are a lot of uncertainties in hydraulic conditions and the development of biofilm, which can lead to clogging and short-circuiting within the filter, reducing its performance. As we have covered in Topic 2, upflow anaerobic sludge blanket and expanded granular sludge bed utilizes fluidized granular sludge to achieve SRT-HRT separation and high biomass concentration. The upflow as well as the gas bubble generated suspend the biomass and provides mixing. Healthy granules are millimeter in diameter and result in a high VSS of 20 to 30 grams per liter in the reactor. A short HRT of 0.2 to 2 days is maintained, which means a very small reactor footprint. To start up a UASB or EGSB, it is often helpful to seed with granules from existing plants. A high loading rate is often preferred to get better granulation. Also, higher upflow velocities help select for denser granules. The large granules means high cellulability and good solid liquid separation, therefore good biomass retention. Also, the granules require no attachment media to reach high biomass concentration. In a dense biomass, the short distance between microbes is beneficial for syntrophic relationships. Interspecies hydrogen transfer and direct interspecies electron transfer provides shortcuts for substrate mass transfer and more rapid reaction rate. But a solid capture system is needed to retain the sludge granules lost during granule floating or change of upflow velocity. Moreover, although extensive studies have been conducted to delineate the formation of granules, there is still no definitive answer. AFBR or anaerobic fluidized bed bioreactor is similar to UASB and EGSB in terms of reactor configuration. But instead of sludge granules, it utilizes carrier materials such as sand or granular activated sludge, GAC, to support the growth of biofilm. Because of the similarity in configuration, it has similar pros and cons as UASB and EGSB. As for the carrier, GAC is more desirable despite the high cost. It can better support the biofilm development due to its irregular surface and its ability to absorb substrates, which creates a high local substrate concentration. Again, we have only covered a few anaerobic systems. There are many more with unique configurations and various advantages and disadvantages. You can use the fundamental and practical knowledge that you have learned in this class to analyze these systems qualitatively and quantitatively.